warm handshake. The way you experience conduction is through touch. So when you touch someone's hand, if it feels cold, that's heat conducting from your hand into their hand. If their hand feels warm, that's heat conducting from their hand into your hand. So touch is one way that we experience conduction. So shaking a warm or cold hand, that process of being in contact, allowing heat to move through material, your skin material, your tissue material. The next mode is convection. So when you think of convection, think of a cool breeze. Or think of this wind chill factor that they report on the Weather Channel. So basically, you experience convection when you experience this thing called the wind chill factor, the effect of the real temperature. What they mean on the weather station is that's not really the real temperature, is that the wind is blowing, therefore it's dragging heat out of your body at an increased rate. So you experience convection by contact with and movement through a fluid, like air or water. Or you could be stationary and the fluid could be moving around you. The third mode of heat transfer that we're going to cover is radiation. And for this, I like to throw out the examples of a sauna or a hot sunny day. That's an example of radiative heat transfer. So if you're sitting in a sauna, you're outside on a hot sunny day, you're being radiated with thermal energy. Now, you experience this. Why do you get radiated? You know, radiation is one of the concepts that we'll devote significant time to and the students struggle with because it's a little bit abstract. But work with me here. So you experience radiation by being within view of an object that's at a temperature much different than yours. So if you think about that, you think about being in the sauna, there's some element in the sauna that's really, really hot, and you're within view of it. So you can get exposed to the radiation coming off that element. And just like the sun, everything on the planet, when the sun is up, it's daytime, is exposed to the sun so that it's within view of this sun that, as we will learn later, has an effective temperature of about 5,860 degrees Kelvin. So it's much, much hotter than we are, and we're in view of it. Therefore, we experience thermal radiation from it. So that's to give you the qualitative feel of thermal radiation and convection and conduction. Well, let's move towards quantifying. So the way we quantify these heat transfer modes is through rate equations. Now, why are they called rate equations? Well, I'm going to show you the equations in a second, but these equations characterize the rate of thermal energy transfer, which, as we discussed, is proportional to the degree of non-equilibrium in the system. And this rate of thermal energy transfer Right? We're talking about a rate here, so we're thinking about energy over time. Right? So our units for energy are joules. That's what we'll use throughout this course. And time, of course, is seconds. So joules per second. That's what a rate is. So when we talk about a rate equation, we're equating joules per second, which also is watts. So this watt unit will be one that we will use frequently in heat transfer. So we talk about heat flux, we measure these things in terms of watts. So basically, these rate equations characterize the rate of thermal energy transfer, energy over time, or watts, in terms of system parameters. For example, geometry, flow conditions, be turbulent or laminar flow, comma, material properties, and the degree of thermal NE, and that's non-equilibrium. So the rate equation balances the rate of thermal energy transferred in terms of system parameters, material properties, and the degree of thermal non-equilibrium. So let's start with conduction. The rate equation for conduction is called Fourier's law. It's called Fourier's law. Fourier's law is written as such. So we have this Q, conduction. This Q represents heat rate. And the units on heat rate are joules per second or watts. So heat rate equals A, the area, times this parameter K, times the change in temperature with position, or the temperature gradient. So this is the temperature gradient, the degree of non-equilibrium. This is K. Thermal conductivity. We'll talk a lot about this parameter, but it's a material property that characterizes or is proportional to the heat rate. And then we have system geometry, A. Important to conduction and the Fourier's law is thermal conductivity. We'll talk a lot about what the origins of it, but basically you can see here there's an interplay between area, thermal conductivity, and the temperature gradient, or the degree of thermal non-equilibrium. So next we have convection. And convection is characterized by Newton's law of cooling. Right? So Newton, you're familiar with Newton, and here he shows up again in heat transfer. So our Q, convection, equals this parameter H, which we'll talk about, times the area of a system, times this temperature difference, where here this Ts is the surface temperature, and this T infinity is the ambient temperature. So